So again, these are sort of a collection of my favorite items, things I find that are programmatically useful to me, things I find that come up over and over again, or things which I see people ask more than once. So the first one is going to be the seek command. As you may know, the seek command takes a second argument, which is the increment. So I can produce all the numbers from 0 to 1 incremented by 0.1. I happen to know, we all probably know, there's 11 numbers in this set because I've included the 0. But suppose I didn't know that there was 11. I could ask for specifically 11 items. And this is, I still think, a relatively new feature of the seek command, but I find it a real time saver. And it's not just a time saver, it helps me avoid a problem, which is that if you ask someone how many spaces there are between 11 posts, not everyone's going to say that there are 10 spaces between 11 posts. It's quite often these are called off by one errors or fence post errors, and it's quite easy to make those when you're programming over and over. The old way I would have done this would have been to work out what the increment is myself, and if I want to produce exactly 28 entries, then I have to remember that it's 27 spaces between them. So to divide the distance between top and bottom values, I need to divide by 27, not 28. So I can avoid that whole potential mistake by simply using the num_elem entry. This also, I think, helps in the sense that it's possible if I had really nasty A and B values that I could get some round-off error if I had enough points. And I might actually miss the last value because if it went slightly over, then it wouldn't be still in range and it might not be produced. So it might get like only 27 values. By using the num_elem, you're sort of guaranteed to get 28, well, guaranteed to get the first and the last and then the right number in between. So I find this a very useful syntax.
Dave, quickly, there's a question from Scott Gold to compute a sequence from 0 to pi using num_elem equals 10. Can we quickly demonstrate that?
Sure. Well, to pi, I'm not sure how many elements.
10.
Yeah.
But
so
text mode now.
Pardon?
You're in text mode for entry.
Oh, thanks.
I think you'll need to have left the pi.
I have to have left that, so we'll see what happens. Is that what was wanted? It has to be numeric, right? For seek to work at all. Anyway, perhaps that was the question. I'm now going to create a list from S. Creating a list from a sequence, really easy to do. Just wrap it in square brackets. There's no real cost to either adding square brackets to turn a sequence into a list or doing the reverse, taking a list and taking off of it to get the sequence. Those are both very cheap operations, and so one never has to worry about inefficiency there. But I'm gonna map a command over both of them, and this mapping command I'm going to use what I call a user-defined procedure or an anonymous procedure in this case because I haven't assigned it to any name. So x goes to x squared, but I'm also going to show you that instead of going x squared, I could use the sort of the prefix form of the power command. So the prefix form is caret, and then the 2 is the exponent. So x is the first argument, 2 is the second, and it produces the same result. But the reason I'm showing you this is I want to show you what commands are used. And the reason is because I could also do it this way, where I'm mapping this command over L and this the 2 gets passed as a second argument. So anything after the list gets added as extra arguments to the command. So it looks a lot like this for the individual entries. It's a useful syntax. The reason that I like this is if I have a huge list, since this is a built-in function in the kernel, I avoid all use of user-defined functions. I don't have to call my own procedure every time. By using only kernel built-ins, I can get a lot more efficiency out. Now, for a huge number of items, the actual cost might even be twice as much just to do it wrapped in my own user-defined function, as simple as it was. It's still a very fast operation, but if you have 10 to the 7 entries or whatever, you could find that you actually double the time or take a performance hit simply by adding that extra function call in there. Now I'm going to map this function. So it takes M and it takes op11. Now op11 of these are matrices. Op11 of a matrix is the first dimension. So 2 and 3 in this case. But if I want to use the kernel built-in only version of that, now I need this to be an argument. It's an extra argument, but it must come before the container instead of after it. Over here, it comes afterwards, and I just tack it on the end. If I want to have it come in front, I use map2. The 2 means that there's an extra argument in front of the list container that's actually going to be mapped onto. In fact, I could also use map3 if I had 2 extra arguments that I wanted to push in front, and so forth. But I'll get the same result. So here is the kernel built-in only version of this. So kernel built-ins only versions of map, great if you can do them. I'm going to do one more item here. I'm going to do the same operation, but I'm going to use the element-wise operator. The element-wise operator is an operator followed by a tilde. So I'm going to use that caret power operator, and I'm going to map it across L. And since the 2 is only a scalar, it gets added as a third argument. I can do the same thing if this is my operator. So it's the same function I used before, and I'm mapping it onto L. But now I'm going to try doing that operation with F and G as the functions. Sorry, as the extra arguments. And what happens is that it doesn't put the list F comma G as the extra argument in front. What it does is it interleaves the 2 lists. So this is a list or R table, and this is a list. So it interleaves these 2 items with the pair of items in L2. So in other words, it's acting like zip. What I'm trying to get at here is that sometimes tilde element-wise operators act like map, but sometimes they act like zip. Sometimes they act like something actually quite different. The point being that you really need to know all of them if you want to get the full functionality. Map is a very important command to know. Zip is an important command to know. The element-wise stuff is really good, but it's very important, I think, to keep in mind that it's not always exactly the same as map, and it's not always the same as zip. It has a bit of a flavor of both under certain circumstances like these. So sort of really good for your tool bag to sort of know them all. Another thing that I really like about the tilde is its the element-wise stuff is its performance. Suppose I have a million entries in a vector, a row vector, and I'm going to map the sign command onto that. It's not just a numeric row vector, it's a numeric row vector where all the entries are hardware floats. It's very, very fast to do this. And in fact, if I try it with map, I get a significantly longer time to compute it. And the reason is because the tilde sign picks up the fact that it's a float8 data type and uses eval HF mode to apply the sign function, which is much, much faster. Whereas when I just call map, it doesn't do that because I didn't ask for it. I have to ask for it specifically to use eval HF when I use the map command. So then I can get a performance. But I think it's really nice that the element-wise operators, if they can use eval HF and they detect a flow date component in our table, a vector or a matrix or an array, then it will use it. And so I find getting that performance increase means that you can sort of build up really nice conglomerations of these tilde element-wise operators, and they're very efficient sort of out of the box without you having to do extra work and think about eval HF and all that. If it can do it, it does it. And I find that to be a really nice efficiency handle. As I said, element-wise operations are not all the same as a map call, and they're not all the same as a zip call. In the first example, I'm using the third argument, not as an extra argument that gets passed to everything. It gets passed by zip as the default fill-in if one of the lists isn't the same length as the other. In this case, the second list is missing an entry, and so it uses P as the fill-in value. So the P appears here because there wasn't a second entry in the second list. But if I was to try the same sort of thing with the tilde operator, it would object because all these aren't the same, and this doesn't match any calling sequence of the tilde mapping of Q. If I map this onto two lists that are the same length, then the extra argument gets passed as an extra argument to each function call. So it doesn't get, it's not like zip, it doesn't use it as a default value. If it needs to as fill in, it actually adds it as an extra argument. So this call and this call are really quite different in behavior from each other. The other thing that zip does is it allows you to intermesh more than two things. In this case, I can map the function, unknown function G across three lists, and it will take one item from each. So I get all these pairs. So the tilde operator doesn't really act like that. But the tilde operator does allow me to do something slightly different, which is put in an extra argument. So I can put in an extra argument between these. Since this isn't a container, it simply gets inserted as an extra argument to each call. So again, zip, map, and tilde operators, all slightly different, but all really good to know.
All right, Dave, we're coming up on the end of the time limit.
Okay. I will simply show that there's a few other functions that do iterative mapping on things worthwhile looking at in the health. Relatively new functions, the reduce with the plus and the scan allow you to do some iterative sort of accruing across lists where you do it either for the whole list or all of them. And my last example is to notice that map also acts on expressions, not just containers. So I can map something onto a product. And if I map it onto a product, then the result is a product. If I map it onto an addition, then the result is also a sum. And if I map it onto a list of items, I can map a function like print and get them all printed on each line. So that's 4 different calls to print. The return value is the empty list because print returns null. If I didn't want to see the empty list, I would suppress that output. The input was a list, so the output is a list. A little bit more additional reading, a couple of other really exciting iterative type functions that are good to know about in Maple or have some functionally related, fold and select reduce. That's it for today. Any questions?